What does y is equal to sine of x look like? It's a wave where, what is the sine of 0? 0. What's the sine of pi over 2? 1. And so you get basically something that kind of looks like this. Is that even or an odd function? It's an odd function. And indeed, nearly every trig function is odd. The sine of x is odd. Y is equal to the reciprocal function. What's a reciprocal of sine? Cosecant. So y equals cosecant of x is odd because it's just the reciprocal of the sine function. And so if sine is odd, cosecant is odd. Next, let's do y is equal to the tangent of x. And you've got a tangent graph, at least the center period, that looks like this. That green tangent graph, at least one period of it, is also symmetric to the origin. It is also odd. And last but not least, we've got y is equal to the cotangent of x. You have an asymptote at x equals 0, an asymptote at x equals pi, and the tangent of pi over 4, cotangent of pi over 4 is 1, cotangent of pi over 2 is 0, cotangent of 3 pi over 4 is negative 1, and you have again that asymptotic behavior. Now, the red cotangent is probably looking like a spaghetti by now, but this is all to remind you of the even and oddness of your trig functions. If we take that graph and we rotate it 180 degrees, it's once again going to be symmetric to the origin. So all four of these trig functions have the same characteristic of being odd, which means that with some limitation, the restriction on your inverse trig functions are going to be basically all the same. Not exactly the same, but very, very similar. We are talking about inverse trig functions. And none of these functions are one-to-one. None of these functions will pass both the test, a vertical line test and a horizontal line test. These are all functions. Every individual value of x will yield one individual value of y. So one x in, one y out, or one domain element in, one range element out. But none of these functions, because they're periodic, for one thing, are going to pass a horizontal line test. Yeah. All of these four functions need to be limited somehow so that their domain is, some will include there are going to be slightly different restrictions, but they're all going to be very similar to a restricted domain of negative pi over 2 to positive pi over 2 so that they act one-to-one. Now, whether you're looking at the black, orange, green, or red graph, all of these are passing a horizontal line test. Now that we have a restricted domain-ish for these four trig functions, we can recall what we get from an inverse trig function. Like, if you grab a calculator or look at the unit circle, the sine of 150 degrees or the sine of 5 pi over 6 is what? You're supposed to know the unit circle. Sine's in quadrant 2, and sine is based on y, so it's positive 1/2. Well, we do need a unit circle quiz. The sine of 5 pi over 6 is 1/2. Great, but if you do the inverse sine of 1/2 from technology, from a calculator, or just following the restrictions of your inverse trig functions, you will not get 5 pi over 6. You will get what? Pi over 6. So yes, functions and inverse functions are inverse math operations. They quote-unquote sort of cancel each other out. But if you have to restrict the domain of the original function so that the inverse is a function and not a relation, you may put an angle into a trig function, get an answer. Again, sine of 5 pi over 6 is 1/2. Try to get back to the angle measure, and you'll get an angle with a similar characteristic, but you may not get the same angle. The inverse sine of 1/2 is pi over 6. What's the similarity between pi over 6 and 5 pi over 6? They have the same reference angle of pi over 6. So not a totally random different answer, but you may not get the same answer. So we have arcsine. You may not see a fraction, but if you see arcsine, you know what are you putting into an inverse trig function? Parts of a reference triangle, a right triangle, and that will be the sides of y over r. And you're going to get theta between negative pi over 2 and positive pi over 2. If you put in arc tangent or inverse tangent, whether it's a decimal, whether it's an integer, whether it's even, I don't know, e, whatever is in here, decimal, integer, or fraction, what do you put into an inverse trig function? Two sides of a right triangle. And for arctangent, that is, of course, we know y over x. And you're going to get theta between negative pi over 2 and positive pi over 2. But we have to remove the sort of equal signs that we see in the restricted range of arcsine, because the tangent of pi over 2 and negative pi over 2, the tangent of any angle whose terminal side is on the y-axis, is going to have a denominator of 0 in their answer. So that's not inclusive. Arc, let's see here. Arc cosecant of r over y. Let's look at this for a second. Remember, this is y is equal to sine of x. This is what y is equal to cosecant of x looks like. What is the restriction of arc cosecant? You're going to get theta measures that are between what? Negative pi over 2 to 0, but there's an asymptote there. So you're going to get from negative pi over 2 to 0, and then skipping over the vertical asymptote, you're going to go from 0 to pi over 2. And we'll have the same restriction basically with arc cotangent, right? Y is equal to the cotangent of x looks like this, at least two periods of it. You restrict the domain to be between negative pi over 2 and positive pi over 2, so that function's 1 to 1. And what are the restrictions for the arc cotangent? Negative pi over 2 to 0, or there's an asymptote, you have to remove 0 though. And from 0 to, same thing. So arc cotangent, what do you put in arc cotangent? X over y. Out comes an angle measure that is going to be greater than or equal to negative pi over 2 and less than 0, or greater than 0 and less than or equal to pi over 2. And the other two trig functions are even. Cosine is an even function. Cosine is symmetric to the y-axis. Cosine, to be made 1 to 1, what part of the domain do we need to cut out that's most convenient, closest to the origin, and doesn't deal with any negatives if possible? We need to restrict that domain to be from 0 to pi. Okay, you're making me feel like you don't remember anything from trig last year when I was your teacher. So arc cosine, what parts of the triangle do you put in arc cosine? X over r, and you're going to get out a theta measure that is between 0 and pi. What's the reciprocal of cosine? Secant. So if on top of this I graph y is equal to secant of x, the reciprocal of 1 is 1. The reciprocal of -1 is -1. And as you get closer to 0, so what are we approaching? Infinity. So arcsecant is going to give you an answer that's going to be what? If this orange graph is the graph of secant, we're going to start at 0 and go to, we have an asymptote where? At pi over 2. Oh, I did ask you a question. Dang, I said I wasn't going to do that. Theta is greater than or equal to pi to 0 going up to pi over 2, and then pick back up on the other side of pi over 2 and go to pi. Okay, we're going to need to remember all of this because, yes, we are learning how to take a derivative of an inverse trig function, but if we have no idea of what's really happening behind these formulas, you know, what's the point? Y is equal to the arcsine of x. And I want to know what y prime is. Yes, you just copied all these formulas down, so you could look at your paper and just tell me. But you just copied down like 34 formulas, even though I wrote 35 after 33. And you know, that doesn't even include memorizing first derivative test, second derivative test, you know, the kinematics of particles in motion about speed is the absolute value of velocity. The derivative of position is velocity, derivative of that is acceleration. Speed increases when acceleration and velocity have the same sign. I mean, there's a whole slew of stuff that you have to have in your memory banks, which I haven't tested that lately, beyond just those 34 formulas. So you're taking a test and you forget this formula. Or you're not sure, you know, something about the formula. You know the gist of it, you know like 90% of it, but you're just not sure about the order of the subtraction in the square root. How do you rederive it? I'm not going to derive 6 formulas for you, but and arguably you can only memorize. You can get away with just memorizing 3. But do we know, if you were not looking at the formula sheet you just made, what the derivative of arcsine is? Of course, the answer is no. But what you do need to realize is that if you want to recreate this formula, you're going to have to remember a few things. You're going to have to remember what it is to do implicit differentiation, and you're going to have to remember the foundations of trig. What do you put into a trig function? An angle. And what do you get out? Okay, make me feel better. I just got a little chilly there. So if this is arcsine, what does this x represent? 2 sides of a right triangle. And so this will come into play in a second. This is going to be 2 parts of a right triangle. I know it just says x, but if it's an inverse trig function, that has to be 2 parts of a reference triangle. And what is the y? It's an angle measure. Okay, so let's keep that in mind. And again, ask yourself, do we know how to take the derivative? Do we know what y prime is? And of course, I want the answer. Even don't look at your papers. The answer is no. So we want to rewrite this equation into a format that we do know, which is we know how to take the derivative of sine. What's the derivative of sine? Cosine of x. So let's take, did I just say, yeah, okay. Let's take the sine of both sides, and we get the sine of y is equal to the sine of arcsine of x. Now, a few minutes ago, when I was still excited about your answers, I said, what's the sine of 5 pi over 6? And you said 1/2. And then I said, what's the inverse sine of 1/2? Even though we started with 5 pi over 6, we got pi over 6. So you have to be within these restrictions for a trig function and the inverse trig function to just cancel blindly. But that is when the sine is on the inside of the composition and the inverse sine is on the outside. With this one being arcsine on the inside of the composition, sine on the outside, they will just cancel, and you don't need to worry about those restrictions we just talked about. So the sine of arcsine does cancel, and we have the sine of y is equal to x. Okay, I am asking for a derivative. I am asking for y prime, and we have absolutely at this point in the year learned how to do implicit differentiation. We don't need to have y by itself to take a derivative. So I'm ultimately trying to find the derivative of y, dy, dx, y prime, whatever you want to call it. Let's do that now. take the derivative of both sides with respect to x, and we get the derivative with respect to x of the sine of y is equal to the derivative with respect to x of x. So you just told me correctly. Thank you. What's the derivative of sine? Cosine. Now that's the outside function. The inside function is not a perfect match. We have an inside function of y, and we are taking a derivative with respect to x. We are doing implicit differentiation. We need to finish the chain rule. So the derivative of the outside function sine is cosine. Now we need to finish the chain rule and get dy over dx is equal to, what's the derivative of x with respect to x? Just 1. When you're doing implicit differentiation, when are you done? You have to get y prime by itself. So we have y prime, or dy dx, is 1 over the cosine of y, which is a correct formula, but it is not the formula that you're going to see on a formula sheet, the formula that you're going to see on a, say, a multiple choice answer for some kind of standardized test or any test for that matter. So you're going to see an answer that is not in terms of trig. You're going to see an answer that's in terms of algebra. That's where you need to remember the foundation of your trig studies. What do you put into a trig function? An angle measure. And we're starting, even though I'm pointing down here, which I'm going to need this, we need to kind of come back up here. We need to come back up here to the original problem to understand how to write this answer that's in terms of trig in terms of algebra. So trig is a study of what? Right? Rotation or angles and reference triangles. So let's, for convenience sake, draw our angle in quadrant 1. What is the name of this angle? Looking at this equation. What's the name of this angle? Y. This is an inverse trig function. So the triangle parts are going in and the angle is coming out. This is angle Y. And then set up your reference triangle. And what parts of the triangle do we get put into arcsine? Or maybe better, the sine of theta is, the sine of y is, now here saying the x, y, r ratios don't kind of make any sense. So, ka, toa. So, angle in, what comes out? So, ka, toa, opposite over hypotenuse. So, when we see this x and our knowledge of trig tells us that this is two parts of a right triangle, the opposite leg is x and the hypotenuse is 1. And for those of you that go into Calc 2, near the end of Calc 2, you're going to learn how to do integration by trig substitution. This is effectively like a trig substitution, but in reverse. Instead of going from algebra to trig, we're going from trig to algebra. A squared plus b squared equals c squared. Pythagorean theorem will tell you that this leg, this adjacent leg, is the square root of 1 minus x squared. Thus, if y is arcsine of x, y prime is 1 over the cosine of y. We've drawn a right triangle. We've drawn an angle in the reference triangle off the given information, given off the example. The cosine of this angle, the cosine of y is adjacent over hypotenuse. The cosine of y is the square root of 1 minus. Here we go. We've got the derivative of arcsine is u prime over the square root of 1 minus u squared. And what's the derivative of sine? Cosine. What's the derivative of cosine? Negative sine. And what's the derivative of cosecant? Negative cosecant of u, cotangent of u, u prime. What's the derivative of cotangent? Negative cosecant squared u times u prime. So we're going to keep that pattern going, that all the cofunctions have a negative derivative, but unlike similar and negative, they're like exactly the same in negative. So the derivative of arc cosine of u is the exact same formula as the derivative for arc sine, but u is negative, u prime in the numerator is negative instead of being positive. The derivative of arc tangent of u is u prime over 1 plus u squared. The derivative of arc cotangent is negative u prime over 1 plus u squared. The derivative of arcsecant of u is u prime over the absolute value of u times the square root of u squared minus 1. And the derivative of arc cosecant is the same thing, but with a negative u prime again in the numerator. Do remember to try and memorize all these rules. And really, arguably, again, the only three that you truly should be memorizing are your derivatives of your primary functions. Not the co-functions, but the primary functions. The derivative of arcsine, the derivative of arctangent of u, and the derivative of arcsecant of u. I do say that out loud. I will say, though, College Board does not have a habit of putting questions about secant or cosecant on their test for some reason. But just for safety's sakes, let's make sure we memorize those derivative rules as well. So we only got 3 examples up here, and we're going to move into integration, which does generally tend to be, as you've seen, a little bit harder than derivatives. If f of x is 5 arc cosecant of 3x, then of course f prime of x is going to be equal to 5 times the derivative with respect to x of arc cosecant, which is the same, we know, as inverse cosecant of 3x. I don't like doing full-blown or any u substitutions when dealing with derivatives. I just say u substitutions for integration, but you might find it, you probably will find it handy to identify what your u is, let u be 3x, and then du, or u prime, is going to be what? Just 3. Just so you know like how to place things in the derivative formulas. And if you know the formulas, these problems do go quite quickly. Unless you got to deal with like maybe product or quotient rule, which might include some of our work up here. So 5 times, what's the derivative of arc cosecant? Negative. So negative u prime. If u is 3x, u prime is 3, so negative 3 over the absolute value of u. So that'll be the absolute value of our u, which is 3x, times the square root of u, 3x, minus 1. And say we have negative 15 over, bring the 5 in, negative 15 over the absolute value of 3x. The 3 is already positive. We could cancel that with the 15 as well, but I'm going to leave it negative f prime of x is negative 15 over the absolute value of 3x times the square root of 9x squared minus 1. What are we going to do for if f of x is arc cosine of 2x? To find f prime, what sort of overall process do we have to go through? Quotient rule. All year I've been telling you that, for one thing, if you only have one term in the denominator and it's a simple algebraic term, to, if possible, take that complex function and split it up into multiple parts. But of course, there's one term in the numerator and one term in the denominator, so that's not happening. What's that quotient rule again? Low. Nice. Low d high, so we're going to be taking the derivative with respect to x of arc cosine of 2x. Low d high minus high d low. I know a lot of you can just rattle this up, probably just write the answer, but I'm writing this up here for notes. That's why I needed more space. So low d high minus high d low over low low. So take a minute, finish that up. For arc cosine, what is our u in this arc cosine? 2x. And so just a little footnote up here. If u is 2x, then u prime is 2. Good. So tell me what to tell me what to write. What are we going to write up in here? X
times negative 2 over 1 minus 2x squared.
over 1 square root of 1 minus 2x squared. And thank you. You want to keep going? What's the rest of this going to be? I think you can do it. So arc cosine of 2x, and the derivative with x with respect to x is 1. And then that is all over x squared. Yes, ma'am. So this is not a free response question. None of these are. They're going to be multiple choice style problems. So I'm just thinking maybe you might see this as two separate terms. We've got a negative 2x over the square root of 1 minus 2 squared. 2x squared is 4x squared. That's all going to be over x squared, and I'm running minus arc cosine of 2x over x squared. Now, when you start dealing with fractions that have like a fraction in the numerator or another fraction in the denominator, when you have like fractions within a whole fraction, you should make everything what? Well, it should make everything look like a fraction, and you have the entire numerator divided by the entire denominator. And we don't really divide by fractions, we what? We multiply by the reciprocal. So when you flip that division of x squared up as a multiple of 1 over x squared, you have an opportunity for a little bit of cancellation. There's one base of x in the numerator, and there's two bases of x's down here. So all this is going to simplify negative 2 over x times the square root of 1 minus 4x squared. And that is going to be f prime of x. So our last example, we have f of x is equal to the cosine of arcsine of x. What do we have in this first term? Chain rule. Nice. Who said that? It's a composition. It's not cosine times arcsine. It's the cosine of arcsine of x. This is a composition of functions, so we are looking at the chain rule for our third example, at least for the first term. And what do you always need to do with logarithms before you take a derivative? Expand them. So we have f of x is equal to the cosine. And by the way, you can write inverse sine of x. That is equivalent. I just don't like it. But it is standard notation. I'm going to throw it in there just to let you see it. This is the minusing one term. Well, that's going to go from minus one term to minus two terms. So make sure that you include parentheses to carry through that negative. You have a division with the like base of e. And logarithms give you what? Exponents. When you have a division of like bases, what do you do to the exponents? You subtract them. So this is going to be, I know you know that, the natural log of x minus 1 minus the natural log of x plus 1. Distributing the negative through here, we're going to have negative natural log of x minus 1 and plus the natural log of x plus 1. And so f prime of x, what's the derivative of cosine? Negative sine. Wow, one person. Okay. Negative sine of arc sine of x, right? And when you do chain rule, you do the derivative of the outside function first, leave the inside alone, and then take a derivative of the inside function. So the derivative of cosine is negative sine. Leave the interior or the composition inside function alone and then take its derivative. So what's the derivative of arcsine of x? 1 over the square root of 1 minus x squared. And then minus, what's the derivative of natural log of u? U prime over u. So the derivative of x minus 1 is 1. So minus 1 over x minus 1, u prime over u on your quiz the other day. And the derivative of natural log of x plus 1 is another 1 over, but this time plus 1 over x plus 1. And somebody would like to maybe do a little bit more simplification. That is right, but front is, I think, wanted me to write one more line. I said I wasn't going to simplify anymore, but there is one more step of simplification I think we do want to think about. Sine of arcsine. The sine of arcsine, these inverse trig operations are going to do what? They're going to cancel out. Were you looking at that? Oh, well, you made me look back at it. That was good. So let me correct myself. F prime of x, or go a little bit farther. Negative x, so negative x over the square root of 1 minus x squared minus 1 over x minus 1 plus 1 over x plus 1. That is more like it. All right, so I'm going to